That's pretty cool. We did have some projects. That's okay. Still about to infect the things. Yeah, that's like.
Okay, we should start. I know some of you are still eating, but there's evaluation time, so you'll have time to eat while we do that. So basically, what we're going to do today is that last time we discussed the experimental task and your strategies and general ideas about categorization. And today we're going to go into the details of modeling exemplar, prototypes, and rule-based models. And we'll see how far we get. We might finish next time. Because before we're going to do the evaluation questionnaires. So let's take 10 minutes. And if in 10 minutes you're not done, we can take a few more minutes. But yes. I'll upload them immediately. Yes. Okay. Are you all done? Good. So now we've done that. We've done that. So this is actually a bit of transparency on how I prepared this class, that I spent a lot of time trying to write meaningful text in the course notes and finding issues with the models through the Bayesian pipeline. And then I asked LLM assistants, and then it completely rewrote my text while I had asked to fix a bug. So that was super annoying. And so when I went and prepared the slides, I ended up doing a big dump of code and plots, which then I realized was kind of boring. So what we're actually going to do is I restarted from scratch. And what we do is we go through the math of implementing these models. And then for the code and the plots, except for a couple that I want to highlight, you can look at the course notes. So, and it's even like today with the proper Blackboard. So that's fantastic. So what we need to do is we need to identify in which kind of scenario we're thinking these models, keeping in mind that the alien that we discussed last time is something that you will have to implement in your assignment. So then we will discuss, and I have to figure out where to stay. We will discuss how these three different classes of models deal with input representation and internal representation, how they develop a comparison of new stimuli to the internal representations, and how they make a decision. And so the experimental setup that I picked is a classic. It's also used as the example in the Bayesian Cognitive Models book by Lee and Wagenmakers, which is a structure developed by Krushke. Basically, you have a two-dimensional space, which is good to start building our intuition. The position, which is the x-axis, and the height of the, I guess, the line inside, which is the, or not of the line, but of the square, which is the y position. And there is a categorization line that goes exactly along the diagonal, which basically means that you can't just rely on either the height or the position exclusively to define whether a stimulus is in category A or category B. And there's 8 stimuli, 2 categories, and in the original experiments, each of the 8 stimulus is presented 8 times to the participant by taking the sequence, shuffling it, presenting it to the participant, shuffling it, presenting it to the participant, and so on and so forth. Here is some code just to redevelop that. We don't need to go through the code. It's just defining the height values and the position values. And the code that I used to generate the experiment. But one of the things that I wanted to highlight is that now we're looking at an experiment which has very specific implications. Which might affect how our model will do. So that's where we need to be a bit careful in designing the experimental tasks, right? We've seen before that, for instance, some tasks in which we were like measuring the binary choice of the participants did not provide enough information to estimate 2 of the parameters that we were interested in, right? In the Bayesian models, it was the total weight and the weight ratio, where with a binary choice, we were only able to estimate accurately the ratio between the 2 weights. Right? What are some of the assumptions that we're making here? So one is that the variation is continuous, which is different from what we see in the alien game, right? That might have a big impact. What is another assumption that this is making? Well, this is making the assumption that the categories never change, which might be something that's fine, right? But it's not necessarily so. So imagine like an elegant jacket. The category of an elegant jacket that changes quite drastically over time. So you need to be able to sort of adjust your category over time. These would not be able to test that. Another thing that you've seen in the alien version of the experiment that you played collectively last week is that there the change is not even as in the concept of an elegant jacket, where it might be a random walk of a sort, but there's actually something that's contingent with how well you're doing changes the rule. After you get 6 in a row correct, the rule changes. Right? And so in the course notes, actually, all of these 3 scenarios are implemented. The static design, a design in which there is a constant drift, like every trials, the boundary shifts, and a situation in which as soon as the agents identify 6 right ones, the rule changes quite drastically. Right? But for the purpose of today's explanation, we stick to 1. I just want to emphasize that the choice of these different elements of your experimental setup, even in the simulation, will have a huge impact on how well the model is doing. Does that make sense? Good. So when we talk about the representational layer, right, we have 3 models: the exemplar, we have the prototype, and we have the rules. So the first point that we have is, as these specific stimuli get taken in by our model, what is the representation of the stimuli? right? How are we passing the stimuli to the model, right? And we discussed earlier that in principle, we could implement a fancy neural network that takes in the pixel and does stuff. But since we don't care about those aspects in these specific projects that we're dealing with in this course, we actually care more about the internal mechanism. So how would you represent this? Yes?
Yeah, XY coordinates.
Exactly, right? In all of them, we're going to have a vector of 2 dimensions per each stimulus, which could be, oh, now I forgot. Yeah, something like the x-axis is 0.4 and the y-axis is, I don't know, 0.4. And then we have the next stimulus, which could be 0.6 and 0.2 and so on and so forth. Right? And that can actually be the same across all 3 models. On top of that, we'll have to define which category it is, right? Which could be a 0 and a 1, right? Whether it's category 1 or category 2. So that part is pretty easy. The second part is once the model gets these specific inputs, how does it create an internal representation that can be used to compare to new stimuli? Right? And we've seen that the exemplars will tend to sort of keep everything in, right? We've seen that the prototype will sort of have a moving average of the different properties of the stimuli. And the zigzaggy thing is, as it sees one exemplar, it's here, then it sees another, it adjusts and adjusts and adjusts and adjusts, right? And we've seen that the rules could be something like height major than 0.5 and position lower, oh, sorry, and position lower than 0.2, right? So how does these translate into a memory, into an internal representation? So in the exemplars, if you could open up the model and look at its memory, what does the memory look like? Yes?
The last 10 exemplars that you see for each category.
Yeah. So it's basically exactly like this. And so it's going to have a matrix of a sort with all the exemplary that it has seen. And then depending on whether we want to implement a limited memory, we might cut it, only the last X, or we might create some sort of exponential decay of the memory. And we'll see the equations in a bit. Now we're just focusing on the representation per se. So if we want at a certain point to add that memory stuff, we might simply add an index, right, that tells us the order in which we've seen them. And then we can do stuff with that later. As we go to the prototype, how would the memory of the prototype look like? Yes?
Just have like the prototype of each, like a mean.
Yes, and how does the mean look like?
Like just a set of coordinates.
So we would have a vector for category 1 or 0. Let's start in order, which could be, I don't know, 0.357 and 0.6 as the second coordinate. We would have that it's category 0, right? And we could have how many steps it has had, and we'll see why. So n of steps. And then we do the same for category 1. Does that make sense? So before we move to rules, right? As we meet, yes. Oh yeah. So how many stimuli we've seen? And I'll get to that in a second why. So as we meet a new stimulus in the exemplar model, what do we do to its memory? Yes. Exactly. So we just add a new step. That's very easy. That's why it's nice for computational people. You just add it, stick it there. As we see a new stimulus for the prototype, what do we need to do? Yes? Yes. How do we update a mean?
We have the number of steps, so you know sort of how much weight on you, so we should have
Yep.
all the steps.
Yes.
And we I don't know how to do, but I remove the XY coordinate space of how much power, like how much
Yeah.
yes, two and three.
Yeah. So now we're saying that we have the new mean of whatever feature corresponds to the old mean adjusted in some way. Anybody has a formula on how we adjust it? Yes. Yes, but let's start a bit earlier, right?
Updated, added, like you were multiplied with a constant, which is 1 minus, and then you're kind of like, I guess the mean or certain.
Okay, I think you're trying to make it more complicated than I want to start. And I think you're right that we want it eventually to be more complicated, but I'm actually thinking of something even more simple. So the idea, anybody else had a suggestion? Yes?
Would they just say the thing to track that? Well, no, we divided by that. Yeah. Yes, and that's got the right setup.
Well, so we've seen when we were doing the matching pennies and our memory model that what we could do you want to, yes?
I was just thinking could be like 1 over n times the New York switch.
Almost. Times, and then it's the stimulus t, right? The problem is that if the mean at time t minus 1 is 0.4, and the position of stimulus t is 0.4, you end up going to a mean of 0.8. Or not actually divided n, so you end up to increase the mean even if it was exactly on spot on. Yes. So what we've done before was to create a prediction error, right? So we would have that the stimulus minus the mean at t minus 1 is our prediction error, the difference between what the mean expects and what we see. And then we multiply that by 1 divided n, right? Or divide the whole thing by n, because the more exemplars we have seen, right, the more certain we are that our prototype is robust. And therefore, we make smaller and smaller steps. And actually, I had sort of spoilered it here. Does that make sense? No. Okay. So the idea is we have a prototype, which is, say, here. And that's our generic idea of what a category 0, let's say a dog, is, right? Then we meet a new stimulus, which is this one. Independently of what we said, whether we said dog or cat, after, our mom says it was a dog. And that means that there is a big difference between what we thought was a dog and what this dog was. So we want to adjust our prototype so that it moves towards the new stimulus. And if the distance were small, we wouldn't want to move it too much. If the distance is big, we want to move it more. That's one dimension. And that's what's covered by this, right? We want to adjust according to how different the stimulus is from our prototype. On the other hand, if we've seen one dog, and this is the second dog that we're seeing, we might want to actually adjust quite a lot. But if we've seen like 100, our family has 100 Great Danes, right? And we see one Chihuahua. Seeing one Chihuahua might be qualitatively mind-blowing, but it's not going to change too much our prototype of a dog. So we might want to move less. And that's what's captured by the 1 minus n. The more experience we have, the smaller the update, no matter the difference. Is this better? Yes, good. So which kind of assumption has these update? Yes? Yes. So it assumes that it can get arbitrarily confident in the prototype by having enough experience. Right? And so you know what a good breakfast is. You've grown up in Denmark for, 25 years or something. And then you go to Italy and they give you cookies. And since you have to navigate cafes in Italy, so you need to be able to adjust your category of a good breakfast, or you get the worst cookies because you just can't evaluate them, right? So this is where this model is implicitly assuming that the categories don't change. If we want the categories to change, that's where the Kalman filter comes in. The idea is we start with a cognitive demand. We are actually quite flexible in developing our categories, right? Your ideas of what cognitive science is change quite a lot in the last 5 years, even if you're developmentally speaking quite old and decrepit, right? What we then go and look is for a tool that allows us to efficiently update a mean position without getting trapped by the without getting trapped by the fact that we've seen a certain amount of exemplaries. So let me just make sure that I do the whole thing. Yes, that's it. Okay, so the way that the Kalman filter works is very similar to what we've seen before, right? We had our memory model, which was mu at times t is equal to mu at times t minus 1 plus, we set 1 divided n by the predictive error, right? What we have here is exactly the same formula, right? But instead of 1 divided n, we put a k. And the k is the so-called Kalman filter, or Kalman gain, actually, which is supposed to take two components into account. One is how confident we are in our prototype. And the second is how noisy do we think that the measurements are? How precise, in other words, do we think that seeing this Chihuahua is actually a good measure of dogs? So for instance, no matter, how confident you are in your, Scandinavian breakfast, right? You might want to be skeptical if you go to the first bed and breakfast and meet like cookies on the table. It might not be very representative of everything. So the formula of the Kalman filter, of the Kalman gain, is the squared variance of, of your previous mean. So how confident you are, divided the squared variance of the previous mean, plus a term called R, which is the uncertainty. If this is the uncertainty in the prototype, this is the uncertainty in the measurement. So it's really nothing else than saying there is a total amount of variance, and how much of that variance is due to our prototype. If we sum up the two sources of noise, how much of that noise is in the prototype? The more it's in the prototype, the more we should trust the predictive error because it's a noisy prototype. The less percentage of the noise is in the prototype, meaning it's in the signal, in the measurement, the less we should trust the predictive error. Does that make sense so far? So if we left it this way, what would be the problem? Yes.
Where do we get the noise of the predicted error?
Well, actually, yes.
The same.
So actually, there's two aspects, right? Where do we get the noise of the prototype? And where do we get the R? And so the noise of the prototype is updated on a trial by trial level, which we're going to see in a bit, the actual formula. The R is a parameter of the model. We could make the model more complex and say that's actually a parameter that should be estimated. But we're going to do it, it's best to have a model that works with a minimal amount of parameters and then you complexify it after. Does that make sense so far? So it's really an attempt at balancing the measurement in the error, the noise in the measurement, and the variability in what you've seen so far. Yes. And after we get feedback, then we want to update the sigma squared. And we do it so that 1 minus k is adjusting our squared variance. Meaning, again, if we have that a lot of the variance is due to our prototype, we don't want to update a lot our estimate of the variance. Right? We know that the prototype is noisy. We're going to keep assuming that it's noisy. If a lot of the variance is instead due to the measurement, we're going to decrease our variance, right, in the prototype. Because we've seen that our prototype is better than the measurement. Right? So we shrink our uncertainty in the prototype. If we see our prototype is worse than the measurement, then we increase our uncertainty. And yes. Okay, so here we again have a possibility of keeping on updating our mean, our prototypes. But what's going to happen is that over time, if the sigma squared is bigger than the noise in the measurement, the sigma square is going to steadily decrease, right? Because you're going to get more and more confident. And that's not going to play nice with the two scenarios in which the rules are changing, right? Because you're going to get unduly confident. So what the other parameter of the model beyond R is going to be is Q, which is an expected change in the underlying categories. Note that it's not necessarily the same change that's happening in the stimuli or in the mechanism that generates the stimuli. It's a parameter in the agent, right? It's what the agent expects to change. And again, in a simulation, we would set it. In an inferential model, we would infer it. So this is really like one of the workhorses in engineering. Yes?
Just say that again about what would you set it?
Oh, yeah, sorry. So basically what we have now is two parameters in the Kalman filter. One is R, and the other is Q. As we simulate data, we first simulate the stimuli, right? And there, we might decide that the stimuli drift in category over time of a certain amount, which would be equivalent to the Q, but in the experimental setup. We might also decide how widespread and close to the boundary the stimuli are, which would be a simulation of the R in the experimental environment. But these are completely separated from what the agent does, because the agent might have very different expectations. So when we simulate the agent, what we do is we decide the parameter values for Q and R. So usually what we would do is we would generate a grid to explore what different R and Q are doing to the behavior of the model in a given experimental environment. When we run participants, if we assume or test that they're using the Kalman filter, what we would do is we would try to infer R and Q from the behavior of the participant in that experimental setup. Does that make sense? And I need to keep track of the what's the time? Sorry, okay, we still have a few minutes. And that's what I do in the course notes, where I sort of run a million different scenarios that we can explore. Okay. And then we can simulate a trajectory of these Kalman filters in these specific static setup that I've shown you. They start at center, and then they see these specific exemplar. So they move completely their representation of the prototype here. Then they see these exemplar, and they move less so, right? And then they see these exemplar, and they move. But again, you can see that their movements related to the distance is shrinking. And until they end up in a specific place, because here we are in a very static setup. If the boundaries of the categories were moving, we would see a different behavior and harder to represent. Good. So, well, we took that chill time at the beginning with the evaluation, so I'm going to keep going for a few more minutes before we take a break. When we get to the rules, we've seen that the stimuli will be represented the same as the exemplars. How are we going to represent the memory of the rule-based agent? It's non-trivial, right? So you're not expected to know, but let's try to think it through. So the agent has played a few rounds. It's met a few exemplars. How does its internal memory look like? Martin? Explain.
Like you have some sort of hinge in the loop that's in places. So like if this feature is bigger than this parameter, then go this way.
Okay, so this would be a multinomial kind of tree, or a tree like those in random forests kind of things.
Yeah, it needs to be the category.
You would have that age, let's say height above 0.5 would send you right,
Yeah.
and height below 0.5 would send you left.
Yeah.
And then you would look here. Oh, here there's another kind of rule. It could be P above 0.2, whatever. I'm making it up. I'm not looking there. And then here you would have category 0, and here you would have category 1. And then you would have, if it's below that, it might be that it's actually P above 0.8, and here it would be 0, and here it would be 1. Does that make sense? Yes.
Is the tree defined beforehand? Well, like when we implement the model, we implement.
Oh, right now we're brainstorming. So that's all roads are possible. Yes.
That is true that there's like a hierarchical structure.
Yes. That's one of the assumptions of that specific model. It's not the only model. It's not the one that I'm going to implement, but this is very common also in machine learning. So we're going to explore it for a bit. Christian?
More of a conceptual wondering kind of thing, but like somehow it seems to me that the root structure is what's updated, but like there is the limit somehow. This should operate somehow on the roots themselves because learning of time.
Yes.
So in this case, yeah, exactly kind of fixed from the get-go.
Martin, do you have an answer to that?
So the little numbers, they would be parameter in the model, so the model learn quite split.
Okay.
And I don't think you need to assume that the features are necessarily hierarchical. If there comes one node in the tree with the age parameter, and then one of the P, and then there will be another here that has age again. And there doesn't need to be a hierarchy of features.
Also, you could imagine it as interaction effect, right? Where the effect of one parameter depends on the value of the other parameter and vice versa.
Depending on the depth of the tree, you don't necessarily have hierarchy.
So these could be parameters. That's one way. Another way that's commonly used in machine learning is you generate a shitload of those, technical term, with random numbers. And then you see how good they are given the training material. Yes?
This is like a visual representation. You couldn't build them up like this. You'd have to have some kind of data structure for it.
Yes.
Would you then do what a matrix is?
Well, you're right on two different levels. So one is we need to figure out a representational format for this, which I don't know if there's a standard actually, Merton, but what I would do is I would say something H major than 0.5 and P major than 0.8. This is one case in which it's 1, right? That was actually minor here. Or H major than 0.5 and P minor than 0.2. That would be equal 1, right?
Okay.
So now we linearized it.
But you still set that like a solution.
Yes. So what's the parameter value? Yes. Yes. So yes, and that's where we're getting in a second. Yes, great. But so what you're saying is what we're doing is we're picking a specific template for the rules, but who's to say that another rule that's H major than 0.1 is not equally a good rule, right? That's your key question, right? How do we decide which representational format to use when the rules can vary in complexity, for instance? Does that make sense so far? The second issue that we're going to get to next time, not today, because I'm not completely ready on that, but is that if we then go and look at all the possible rules, given certain constraints, so it's a finite universe, there's no chance in hell that Stan is going to be able to estimate that because there's just too many possible rules. And so we're going to use a different kind of approach, which is called a simulation-based inference. It used to be called approximate Bayesian computation. Now that we have deep learning, they're calling it neural-based inference, whatever. But it's a way of bypassing likelihood and trying to figure out things anyway. But we'll get to that next week. So our question is, when we open up the memory of our agent after a certain number of trials, we're going to see a certain amount of rules, right, which we can specify as conditions, as we've seen it before. Right? Does that make sense? Yes?
I'm a bit confused about, like, in terms of like code,
Yes.
would it be an if statement? Like if yada yada and this, then it's category 0.
Yeah. Or you can simply say that true is category 1 and false is category 0, right? And that you just have a statement, a conditional statement. Yeah. So independently of the shape of these rules, we might have H major than 0.5. We might have P equal 0.2. It's a stupid rule, but it's possible. We could have H minor than 0.2 and P major than 0.8, right? Let's say it has a memory of 3. And each of these rules, right, is likely not to be equally probable given the data that we've seen. So what do we need on top of that? We don't just need a set of rules. Yes. That could be a ranking, but we've seen other tools that we can use because rankings are tricky to deal with. Yes? It could be a weight, yes. I wouldn't call it attention because you might pay attention to all of the rules, but you update their probability given the data that you've seen so far. So some sort of weight. which tells us which we should trust best. Does that make sense so far? Yes.
If we're getting true and false statements,
Yes.
how do we weight them?
Well, yes, that's a good point. So you could say, well, H major than 0.5 should give you a category 1 is either true or false. But over time, you might see that it's true 3 times and false 2. And so that's going to give you a way of graduating how likely this rule is. Why do we do so instead of strict falsificationism like Popper would have wanted us to do? There's two. So the idea is the rules are deterministic. So we could adopt a very strict principle and say we check, we get one stimulus, is H above 0.5? Yes. So we're going to say 1. If the experimenter or the computer tells us, bah, wrong, we could just throw it away, right? The rule is falsified. Yes. That would be one way, but it's actually even earlier than that. Yes.
Because you want to change the value in your rule to get a better, like put the line somewhere.
Okay, so we might change this, right? But actually, I'm not doing that. Even if we're not doing that, that rule could still be useful. Yes, Christian?
I feel like I'm repeating what maybe has already been said, but just like somehow sort it there. I mean, this is evidence against that rule, but it doesn't have to say that it couldn't be true. That makes I think that's
And why would that be a good strategy?
well, it would be a good strategy that the data itself is not limited.
Good. Point 1. If we're sampling from the categories with noise, right? If somebody told us that that Chihuahua is a dog, if somebody told us that those cookies are a good breakfast, right? We might be a little bit skeptical, right? We might not want to take it at face value. We might say, well, maybe it was an error. That's one possibility. Another is that humans do good enough cognition. What does it mean? It means that the rule, the true rule, might be arbitrarily complex. But if these heuristic gets us right 80% of the time, it might be good enough either generally or until we get a better rule. If we just rule out all the partially good rules, we might not have criteria to pick. And we might not perform optimally because 80% or even 56% is better than chance. Right? So putting a weight helps us keeping this rule in the bag so that we can perform ideally better than chance until we get better. Yes.
I'm just wondering, could there be like an interaction between rules where we might, if we don't like falsify and throw them out, could they like counterbalance each other?
Yes. So the question is, do we get a collective intelligence across rules, right? Do we get better performance by considering a bag of rules at the same time with some weights that we're adjusting and taking the aggregated decision of these rules? And yes, so I can't remember if I pointed to it last time now, but I have a talk on the alien game where I show that actually a set of rules that cannot possibly capture the actual rules that were used to generate the data can actually perform just as well as humans. Right? So even if they cannot, so the rule requires 3 features, even if you only give it rules that have 2 features, by putting them together, it gets to the level above the level of individuals and close to the level of pairs. Right? So just saying that actually it might be a better model of how we work, having these sort of several things that run at the same time. Does it make sense? How do we update this in the specific model or family of models that I want to implement and I put in the course notes? There is a parameter called epsilon, which is an arbitrarily small number. And I want to get the the equation exact. Why didn't I? Okay, I didn't write it down. Huh, great. But let's say that these rule age above 0.5, first exemplar we meet doesn't work. Right? So we give it a weight of epsilon. This second rule, p equals 0.2, which is a crappy rule, but by chance it works, right? We give a weight of 1 minus epsilon. Right? The epsilon could be 0.01, it could be 0.2, right? Depending on how quickly we are at updating things. Then as we get to another exemplar, what we do is if these also keeps being crap, right? We might say times epsilon. Right? And this one keeps being right, so if we say times 1 minus epsilon, there is a formula. I need to dig it up during the break, but there is a formula to increase the specific weight of this rule. Right. And I think that we can take the break now because I'm going to look it up. And then after the break, I'll give you that equation and then we'll discuss. But what if the 3 rules that we started with are all bad? How do we make sure that new hypotheses are generated? If you remember playing the alien game, that might be one of the ways in which you tried out things, right? So you said, oh, I really think it's the raised arms. And then it wasn't. And so you needed to sort of say, okay, maybe I should actually pay attention to the spots. And then you add a new rule. But how do we model this dynamic change of which rules are in the spotlight of attention? And that's for after the break. So let's take 10 minutes break. Yes, just give me a second that I want to pause. Okay, so as you were taking a break, did new doubts come up? Yes.
If it's a tangent, you don't have to answer now. It's just I was thinking about the implementation level. Or really, it's like now. Okay, I'm just gonna say anyways. It's just that I feel like the rule one.
Yep.
Makes so much sense intuitive because it operates at that symbolic level, like essentially language. You can imagine.
Yep.
So I was solving the test. I was doing it like linguistic.
Mm-hmm. Especially if you had had the chance of talking to your group mates,
Yeah.
right? Yeah.
If we take that into account also when evaluating these models, like that the other tools are very abstract and you have like when thinking about the concept of brain interpretation, it gets weird, complicated something. But the other one is very easy to understand concept.
Well, so if you think about a neural implementation, the first ones are much easier to represent. Yeah. Yes. Yeah, no, you're absolutely right. So one of the reasons for which I'm showing all three, it's because they're so different, right? And that sort of pushes us to tackle the fact that there are very different ways of modeling the very same process. But you're right. And in terms of implementation, as we will see next week, it requires different tools than Stan, actually. Okay. Any other questions? Does this make sense? So I know it's a lot, and there's a lot of equations on the board, right? This is not meant to be a standalone, right? You have the course notes that you can look through for the implementations, but I thought that actually running through the math together could help developing an understanding for what we're doing. And we've looked at code a lot in the past weeks, so it's nice to spice it up every now and then. Okay, so what I was saying before is that as rule 1 gets disconfirmed again, its weight gets multiplied by epsilon, a small number. As the second rule gets confirmed, its weight gets multiplied again by 1 minus epsilon, the big number. These would quickly become arbitrarily small, because if both numbers are below 1, it's just getting smaller and smaller. And that's where I was getting stuck before, because I'd forgotten a specific step, which is after we update the weights, we renormalize so that they sum up to 1. Right? So they get brought up to a more meaningful probability space again. Does that make sense? Good. At this point, we might be stuck, say, with 2 rules which are crap, and 1 rule which is only half crap. And if you were to keep on suggesting to your group mates these rules, they would say, get unstuck, right? Let's try something else. How does this work in the model? So there's 2 mechanisms. One is called resampling. And the other is called mutation. The idea is once the variance, well, there's very many ways. So my first implementation was basically saying at every trial, or when a weight goes below 10%. But they're more unstable implementation than what is in the literature. But at least it taught me why the literature is doing it like that, which is basically you look at the standard deviation amongst the weights. And when it passes a certain threshold, tau, you resample. Resampling means you take the distribution of the weights and you sample 3 rules from the very same set of rules according to their weight. So you might actually end up having, say, age major than 0.5 twice, which is suggested in the literature sort of replicate the idea that you become more confident about certain rules. They count for more when you go and make the next prediction. However, this doesn't get you unstuck, if you're in a bad set of rules, resampling amongst those rules still keeps you in the bad rule domain. So after you've done the resampling, for each rule, there is a probability mu that this rule gets discarded, no matter how good it is, and that a new rule is sampled from the universe of possible rules. Right? So to wrap it up, you have a universe of all the possible rules according to some constraints that you put. Let's say you could say, oh, I only want all the possible rules with one feature and parameter values at the first decimal. You could have a second universe that says all possible rules with 1 and 2 features connected by and decimals. Or you could say connected by and or. Right? Yes?
But can the new rule be not like fully random, say, and the parameters doesn't be thrown away? Like,
yeah, that's where I'm getting. Yes, yeah. Great. So, well, that's actually, it's the next step in what's out there because it hasn't been really implemented. But it's a good point that deserves implementation. So you have this big ocean of rules. Your agent, according to a parameter n, how many spaces it has in memory, samples completely randomly n rules. It meets the exemplars, starts updating how likely these rules are given the exemplars. Once there's some clearly that are better than others, right? It resamples, right? It likely increases the number of those good rules, identical good rules in its memory, and decreases the number of bad rules in its memory. And then it randomly samples from the universe of rules again. So if it samples randomly, right, what we might have is that it doesn't get that all the good rules we have sort of have height above 0.5 and then something else, which is not how humans would behave. They might do targeted sampling. It's not in the literature out. I've started having an implementation, but I'll see how far I can get in that by next week, where you can have, for instance, here it's simple, but you could have that the probability of sampling a new rule during mutation depends on how many times a feature appears in the given rules, right? If you have all your rules that have H, then H should be in the rule with a very high probability. You could have a meta level where you have the probability of having rules with 1 feature versus the probability of having rules with 2 features. And the new rules are sampled according to those probabilities. So you can implement it in many ways, and this is a very simple example. So your creativity is limited, but if you think even just the 5 features of the aliens, it becomes very open. Don't go that way for your model, but because you only have 2-3 weeks to implement it. But I'll provide as much code as I manage by the end of the course, so you can see how it works. Does that make sense? Yes.
When we renormalize the weights,
yes,
is there like a specific reason? Like it's because they disappear, or is it because we really want them to sum up?
I think both. We also want them to sum up to 1 because then we already have a decision rule, right? Because we say the decision should basically be the weighted average of the decision of each rule. And then we get it for free. But we could have it go arbitrarily small and then do the decision rule in terms of majority or something else, right? Yes. So by the way, this is where connectionism and Bayes are completely a clash, because in this Bayesian model of how we do categorization based on rules, the rules are pre-existing in a big ocean of all the possible rules, right? And what Bayes is good at is at updating our belief in each of these rules. But where the rules come from, that's not in Bayes, right? So for instance, we might hack a system that says, well, let's count how many features, or let's make a meta level template. It doesn't emerge from Bayes' rule per se. And yep, sorry. And the big point in connectionism was actually that symbolic rules would emerge from just exposure to exemplars, right? And so in the Laws of Thought, that's a book that I've recommended, what Tom Griffith is trying to argue is that you can combine the two with connectionism. You get the formation of these rules and concepts and cluster, but the way that they can be accepted or updated over time is done in a Bayesian fashion or approximating Bayes. Okay, so now what we have as the last really big step is what is called evidentiary evaluation. And I might have anticipated it a bit, but it is, as we get a new exemplar, how do we calculate whether it should be category 1 or 2? Right. And so last time we already seen how it would work for the exemplars, but let's say that you have these metrics of previous exemplar, and you get a new exemplar that says 0.5, 0.5. How do we, actually, let me make a couple more here. So it would be 0.2, 0.2. It's also category 0, and 0.8, 0.8 is category 1. Okay, how do we assess which category the new stimulus is from? Somebody else? Yes?
Like based on the distance, notes, like they're stored.
Yes? Can you walk us through a bit more details?
It's like picturized.
Mm-hmm.
They check like a
Okay, let's take it one step at a time, right? It's vectorized, so we say we take the first exemplar and we say, what's the distance in the two dimensions? It's 0.5 and 0.5. Right? Then we have from the second is 0.1 and 0.3. And then we have from the third, we have 0.3 and 0.3. And again, 0.3 and 0.3. Right, now we have distances, and these two are from category 0, and these two are from category 1. What's the next step? If you remember, oh, do you have a point? We could do Euclidean distance, but remember that we might be more taken by height than position. Right? We might be paying more attention to the one than to the other. Yes. So for instance, this could be 0.8 times, and this could be 0.2 times. And that would be for the whole thing, right? Where we give a lot of weight to the first and less weight to the second. Yes?
I was just wondering about, is there really difference between examples and prototype learning? Because it comes, like, I'm assuming that if you have the right update for prototypes and you have the right distance, then you can replicate any sort of behavior.
Not these. So exemplar does decently at a scenario where this is category 1 and this is category 2, while prototype does very poorly. So if you have more than one cluster, exemplar is better. Yeah. Because if you remember, we're going to now put similarity on top, which sort of discards all of those that are too far. Yeah. Yeah, but with the prototype, you don't have the tools to do multi-clusters. Yeah. That would be the big difference. So you get that computationally, prototype is much more efficient, slightly trickier to update, but very small memory and very quick calculations of which centroid we're closer to. The exemplars has bigger memory, bigger computation, but it can sort of have a wonky space that it describes. Yeah. So now we multiply all these things. So we have, oh, do I really have to do it? But the distance is actually in absolute terms, because if we use the blockwise, then we're going to have actually 0.08 plus 0.02, which is 0.1. And then we have the next is going to be 0.08 plus 0.06. And that would be 0.14. And the next one is 0.024. Yes. Plus 0.06, which is going to be 0.3, et cetera, right? We get a bunch of distances. Yes?
Is it on purpose that we take like the absolute value or like difference, not the...
Yes, because we're interested not in the direction of distance, but just in how distant they are. Yes. So we end up with a bunch of distances from exemplars. And at this point, we might simply sum them up, right? And say, now we look at the sum of the distances between these new exemplar and all the exemplars we've seen of dogs and all the exemplars that we've seen of cats and look at which one is closer. But a lot of cognitive research has gone into showing that the way we perceive similarity and in general, the way that our mental spaces are is not a linear space. Meaning that if I have a new stimulus here, right, these one are going to count less as good representative of these than these one. And that the perception of similarity is going to have an exponential decay. These are not simply twice as distant as these ones, but they're perceived as almost incomparable. right? So usually what we have is then an exponential formula, which I'm gonna bring up to avoid making a mess of it, which is minus e to the power of the distance times an exponent c, which tells us how steep the decay is. And usually we estimate it. So these is, and so what we do is not the sum of the distances, but it's the sum of the similarities. So that being distant from these exemplars is going to really penalize category cats compared to how much these is going to give it a plus. Was there a question? Yes.
What about like the amount of exemplars?
Yes.
And if they're not equally distributed,
Yeah.
maybe there's many more cats.
So this is where I have a slight historical rant, which I think it's fine because then we'll do, so the distances in prototype are exactly the same, just with 1 point. And then we'll do evidentiary stuff in the rules next time. So the idea is that early on, when Nosovsky developed the GCM model, there were a couple of things that really constrain the conceptual space. The first one is that the weights, the attention is static. It doesn't change, right? Which means that if you want to have a good fit to participant data, you should get them to learn the stimuli in advance so that they have well-established attention weights when you start testing. The second is that Nosovsky liked the sum of similarities, which means that if you've met only very few dogs and a lot of cats, the base rate of cats will tend to bias your decision in favor of cats. Right? But you want these unbalanced to reflect the true base rate of the category. Because if you're just sampling randomly, then some participant might look like they're biased in one direction because they got exposed to a lot of dogs early on. And so that, again, makes your model safer if you train your participant well in advance on the proportion of dogs and cats that you actually want to be expressed by the participants, right? Third, if you want to estimate W and C, and you're trying to model a participant who's still learning the categories, that estimation is going to be very difficult because you don't know whether decisions in the early trials where there's very few exemplars that have been experienced is due to more attention there or to a quick decay of similarity. So then again, in order to fit that model, especially with maximum likelihood methods, it's a very good idea if your participants are already trained when they come in, so that you have everything set up from the start. And that's why a lot of, even if this is in principle a model of how we learn categories, there is very little learning in most of the applications of these models, and very little learning in the data that are analyzed with these models. But there's no reason to do that. Now we have actually good tools to fit these models. So for instance, in the course notes, What we do is we model participants that are actually going for the very first time through these stimuli. And the model fits. And we validate it, and it has no issues. Well, it has some issues, but they're due to a different thing, which we'll discuss. The second is somebody decided that the weights should also be learned and develop a model called ALCOVE that use a neural network to do that. The model doesn't validate, so that's a bit bad. But there's nothing stopping you from saying, well, if we update the weights with reinforcement learning, for instance, and you can actually, if you understand the different steps in building a model, even if everybody else has been doing things in a different way, there's nothing stopping you from changing the assumption of the model. You're not bound to a toolbox that's already there. You can actually build the models yourself. With that, we'll stop, and I'll see you tomorrow.